Okay, so welcome to the course, and today we will be learning another new technique that reactively makes one agent avoid all the other obstacles, other agents, robots, and everything. So, let's have a recap about what is reactive planning. I've got my robot over here, and this is the one that I need to decide how does it travel. So whether it goes here, it goes here. Of course, it'll be a function of the nearest few agents around. So these are two robots around. It'll be a function of where the goal is. So I know that probably it should go here, but taking this gap is good. And the static obstacles around. Now, potential field last time we did consider these things up. We considered the repulsion from all the static obstacles around. We considered the repulsion from all the robots around and the attraction to goal. In the socialistic modeling, we also took into account where the robot is heading, where should it be heading, and we had the elliptical model around. But what we did not consider was where are the other robots moving. So this robot is currently going here, and therefore it's not a threat, but currently this robot is going over here, and therefore if I naively go to the goal, I will incur into a collision. And just because I've drawn this v2, the current velocity vector, I know that there's a problem. And if I don't consider this v2, which was the case previously, then this probably looked like a good path. But now that I've considered v2, probably I'm saying that this is a good path to take. So the first approach we will have is what does exactly this thing? It reactively plans based on the velocity vectors of all neighboring agents, robots, whatever you call them. Now, for now, I'm gonna make in a big assumption. So I'll say this is my map and it has no static obstacle. So it's completely devoid of any kind of static obstacles. I have dynamic obstacles which are other agents, however, they are all circular in nature. So that's my R that I need to plan, and it's R1, R2, R3, R4, the other agents. So my assumption says number one, no static obstacles, and number two, all dynamic obstacles which can be robots are circular with a known current velocity vector. Which is fair enough. So people move around and people are definitely circular. Some people are more circular than the skinny students out there. That's completely valid. The robots are mostly circular, mobile robots. Mostly they are circular. Even if they are almost circular, a little bit elliptical, you can actually cast a circle all around them. It doesn't lead to a major loss. Now, this course is not about how do I deal with static obstacles, which is another course at this university. This is all about how do I deal with all the agents which are going around over here, and I need to be able to avoid them given these are their velocity vectors. And of course, I have a knowledge of the goal with me. The assumption that I know the velocity vector is not hard. So we've got another course that talks all about how does a robot keep a track on its own position. The assumption the last hour's lecture as well. How does a robot always know its own position? Using a technology called as localization, and using a very similar technology, it also knows about the positions of all the other agents and their velocity along with time. So what are those algorithms we'll not be discussing, but we'll say that suppose I know all the velocity vectors, all the agents are circular and there are no static obstacles. How do I actually make a decision about where the robot is gonna go? My output is still reactive in nature. That means my output will be limited to linear speed. So there's been a overuse of v, so let me call it as a s. The linear speed, it's not a velocity vector, and angular speed. So let's call it as the omega. Now we'll be dealing with velocity vectors, and my little experience is that vectors are a bit harder to digest, especially after you have been off touch from vectors for a reasonably long time. So let's have some motivation only, and let's do a few calculations quick in hands so that we understand a bit of a concept without the mathematical jargons. So I need to reduce vectors. That means the map needs to be 1D so that everything becomes scalar. So let's take a bit of a 1D map, and the bit of a 1D map looks around like this. So a very narrow map, which is around over here, and this is, let us say, a vehicle. So that's what is a vehicle, and it's going like this at a speed of just 10 kilometer per hour. Okay, so synthetic numbers over here, and because we use meter per second in science, so instead of kilometer per hour, let us say that it goes at a very much smaller speed of 30 meter per second. Random numbers, and it goes in one dimension, so my map is literally 1D, and this is where I am, so that's me, and I need to be able to cross this road, and let us say that this road is just a mere 10 meter. So again, random numbers over here. So if I need to cross this road, I virtually have two options with me. The first option is that I move such that I cross this road much before this vehicle. And the other option is that I wait for this vehicle and to pass by. My question is, at what speed should I cross the road so that no collision happens? So two cases arise. I cross it much before this vehicle goes, and I cross it after this vehicle goes. So in order to answer this question, let me answer the inverse question. At what speed should I cross the road so that a collision definitely happens. And then I'll just say all speeds possible minus this number is this numbers. So now if I need to find out at what speed a collision definitely happens, let me take the two limiting cases and draw them over here. The first one is over here. So the first case is when the vehicle is over here and I reach the spot over here and I end up in a collision. And the second speed, the limiting case is the vehicle is over here and I end up in a collision over here. So all the intermediate speeds is the one that matter to me. And let us again have some numbers. So let the length of the vehicle be just 1 meter. It's a small vehicle, very small vehicle. So in fact, let me increase it. Let me make it as 3 meters. And let us say the current distance from this to the crossing point is uh, 10 is already done, so let's say 20 meters. Okay, so some random numbers around over here. So now for this case, if I look at it, this was the initial position of the vehicle. This is the final position of the vehicle. From what I took, this was 20 meter. I am going straight. This is 3 meter. So how much the vehicle bonnet has, front bonnet traveled, it's traveled a total distance of 20 meter. So the time taken for the vehicle to reach from here to here will be equal to time is distance upon speed, which comes out to be 2.3 seconds. Now, how much do I travel around over here? I travel 10 meter. So in this much amount of time, I travel 10 meter in this much amount of time. That means my speed will be given by distance upon time. Speed is distance upon time. So that means 30 by 2 meter per second is equal to 15 meter per second. So that's case 1. Similarly, let's do case number 2. This is where the vehicle started off with. And if this is where the vehicle started off with, this is 20 meter. So how much the vehicle's front bonnet has traveled? So it has traveled this 20 meter and additionally the length of the vehicle, which is 3 meters. So the time will be given by distance upon speed. So this turns out to be 23 by 30 meter per second. And what is my speed? So how much distance do I travel? I travel 10 meter. And in how much time? In 23 by 30 meter per second. So this turns out to be 300. Oops. This turns out to be 300 by 23 meter per second. This has to be seconds, and this has to be seconds. And this one is what is a case 2. So case 1 is when I collide with the front of the vehicle And case 2 is when I collide with the rear of the vehicle. Now, anything intermediate between these two cases is definitely a collision for me. So I should do anything except for take any case which is intermediate between V1 and V2. So those are the cases in which I am definitely to collide. At one time I'll collide with this point, at another time maybe with this point, at another intermediate case at this point, at another intermediate case by this point, and maybe at another intermediate case at this point. So at all these cases I do end up colliding with at least some part of the vehicle. So these are the speeds at which I am definitely gonna collide, and because they are speeds, let me say S1 and S2, although it's really velocity because of the fact that the scenario is one dimensional only, so I cannot travel in a diagonal direction. I need to travel up in the front direction only. That's a constraint just because I wanted to avoid the vectors.